Hello everyone, it is week 5. I hope you have enjoyed the course material. So in today's discussion, we will cover the confusing concepts in the previous lectures, and then we will start today's discussion about capacitance, inductance, and resistance. Okay? So let's start with confusing concepts. From the midterm, I noticed that some of us are confused about the current source and the voltage source, the properties in the circuit. So I want you to keep in mind that a current source, its voltage is undetermined. We cannot assume that it is equal to 0, okay? Similarly, a voltage source current is undetermined. We need to calculate them indirectly with KCL or KVL. All right. And the second point is our understanding of a short circuit. I noticed that when we want to simplify a circuit in the exam, we often make mistakes about recognizing a short circuit and determining which elements can be neglected. So basically, a short circuit means that if you want to go from A to B, node A to node B, imagine that you are an electron. You want to go from A to B. You will always choose the easier way to go. So if you can go through a wire, which is an ideal conductor, you know you will not go through other elements between them. Here is A, here's B. If they are directly connected by a wire, as an electron, you would like to go this way instead of go the other difficult way, right? So in this way, we say that this is shorted. But some of us make mistakes in the exam in a more complicated situation. For example, if there are two resistances between A and B, we can still determine that these two resistance in series are shorted, right? But what if here is another node called C are connected in the middle? Can we say that R1 and R2 are still shorted between A and B? I will let you know the answer. The answer is no. Because if we are going from A to B, we cannot say that R1 is also an element between A and B, right? R1 is between A and C now. So R1 is not an element connected to A and B, right? So check your understanding. If R1 or R2 are not shorted by A and B, what is the relationship between them? Yes, R1 is now in parallel with R2. And the circuits can be simplified as this. All right, A or B. See here. Okay. And third confusing concept is supermesh and supernode. I noticed that many of you know that we need to apply supermesh or supernode in the network analysis, but some mistakes are made in the process. So let's talk about supermesh first. Let's suppose we have a circuit and there are 3 mesh here, right? We name it I1, I2, I3, 3 mesh currents. But now we have a current source in between. So as we know, we should draw a super mesh here to skip the current source, right? But when we list the equation, we need to be super careful. Let me give some elements. R1, R2, R3, R4, R4. When we try to write down the equation of the supermesh, we need to know that we are still representing the KVL using mesh currents. So here, we keep the I2 and I3. Okay? So in the supermesh, we keep the original variables instead of name a new supermesh current. So, okay? Now for supernode, when we set the reference node here, we will notice that node 1, the node voltage, is equal to Vs1, right? But we should keep in mind that V1 is not equal to Vs2. Why? Because there is a resistance between the reference node and the negative polarity of Vs2, right? There is some voltage across a resistance. So the correct relationship between them should be Vs1 equals to Vs2 plus Vr, right? So keep in mind that node voltage is defined with positive reference polarity as the node and the negative reference polarity as the reference node. Okay? And the last thing to remind you is about the Thevenin equivalent resistant equivalent circuit. So when I was an undergrad, I was confused. Like, is Thevenin an open circuit? If it is an open circuit, why is it connected to other part of the circuit? So the answer is we only assume it is open circuit when we want to compute the VT. And we only assume that it is a short circuit when we want to compute the IN. So when we say it's open or short, they are just our assumption. They're just a condition for us to get our interested properties. And after we get this value, we will draw the equivalent circuits and then put it back to where it was. Which means that if there is a complicated circuit connected to a resistance, after you simplify the complicated circuit to a Thevenin equivalent, you should still connect it back to the original resistance. Okay? For today's contents, we will cover capacitor, capacitance, inductance, and RL, RC circuits. And our goal today is be able to determine the voltage or current of the capacitors, or inductor at 0 minus or 0 plus timestamp, which means right before and after the switch open or close. Okay, and it would be super helpful for your homework. All right, some basic information about capacitance and inductance. Number 1, they all store energy. And second, they are both passive elements. So a passive configuration is preferred. And 3, their property, like IL, is continuous, and VC is continuous, which means that they will not sharply change. Okay, and this is extremely important. It helps us to determine their status before and after the switch change. And when you do your homework, always list these two equations down. Okay? And derived from these two equations, we'll have the integral format, which is also very helpful. Don't forget the initial state. It is very important. It means that the capacitance already stored some energy in it. And same for the inductance. All right? And you observe that because VC is an integral of the I, and IL is an integration of VL. So they will not change immediately. Okay. And from the I and V we will be able to calculate their power and energy. And when the time is long enough, the circuit will reach a steady state. Under steady state, the capacitance will act as an open circuit because no more electrons flows to the plates and the current will be zero. For the inductance, it will act like a short circuit, like a wire. If a capacitance or an inductance is fully charged, which means that they store much energy, and then we connect it with a resistance, what will happen? Yes, the energy will gradually goes from capacitance or inductance to the resistance. And the resistance will transform the energy from magnetic energy or electrical energy to heat, which means they consume them, they absorb them. And then finally, the total energy will become zero. If we sketch them, we will see a curve like this. And when we connect them with a source, things will be a little bit different. If it is a voltage source, for this, we usually write down a KVL function. For this, we usually write a KCL function at the top node. Let's try to write it down. And we know that I equals to IC equals to C, the derivative of VC. And we substitute this into the original KVL function, we will get Vs equal to RC dVc over dt plus Vc. Okay? And let's divide both sides by RC, we will get. This is the same as a general form. And for the second example, we write KCL at the top node. The current flowing into the node equals to current flowing out of the node. And we know that the I here equals to VR over R. And IC equals to this. And we also know VR equals to VC. Then we get divided both sides by c, we have, right? So we get the first order equation of VC. They are basically differential equations. And here are the methods on calculating the differential equations. Our solution will be divided into two parts. The first one is particular solution. The second one is the complementary solution. For the particular solution, we will discuss what is the FT. In the first equation above, FT equals to Vs over Rc. In the second equation, it is equals to Is over C, etc. So it depends on what your equations look like. And if the FT is a constant, which means that the circuit is a DC circuit, we will guess that XP is in the form of a constant. Let's name it an unknown variable A. And then we substitute it into the original circuit, in the original equations. For example, in the first equation, it will turn into dA dt plus RC, 1 over RC, A. And because A is a constant, this will be 0 plus RC over 1, A Vs RC, right? And we will get A equals to Vs. And if Vt is in the form of sine omega t or cosine omega t, which means that it is an AC circuit, we will guess XP is in the form of A cosine omega t plus B sine omega t. Okay? And this time, we will still plug it in like this. Let's solve it together. The derivative of cosine omega t will be minus omega sine omega t. Okay, to simplify the problem, the omega here is 1, the same as the omega for sine t here, right? So it will be, right? Nice. And then we can list the equations for sine t and cosine t separately. Okay? This is for sine, this is for cosine, right? And eliminating the sine or cosine part, we get the relationship between all these coefficients. And then we will get the answer. A equals blah, 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 P equals to blah, 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 right? And we will know the RP now. For the complementary solution, it is always in the form of K1 E minus T over tau. Tau is a time constant. And it represents the transient response. And this term will disappear as time goes to infinity, long enough, which is also the steady state. Okay? So we get tau. Because it is first order, right? So we only have one storing element. And the K1 can be obtained by initial state. For example, because we already know XP and we still have K1 undetermined. And then we plug it in for time equals to 0. So the T is 0 and this term will become K1, right? And we know the value of X0. Then we can solve for K. Yay! This is basically how the solving equation works. I'll give you an example about how to determine the first order circuits, their status before and after the switch is open. Okay, at the beginning, the switch is closed for a long time. And when t equals to 0, the switch opens. Now I want to ask, during the instant right before the switch opens, what is VCE? What is VC1? What is VC2? And what is I1 and I2? And I also want to ask, in the instant right after the switch opens, what are the two capacitance voltage and the current flowing through elements? Okay. I'll break it down step by step, and all of you will be able to solve it. First, let's consider the situation before the switch opens. We know that before the switch opens, it has been closed for a long time, which means that it is a steady state. So long time means steady state. And remember, what is a capacitance equivalent to when it is steady? Yes, it acts like an open circuit. So it will be a good time to redraw the circuit. It is open. Switch is closed. Capacitor is open. Great. So let's further remove the unnecessary wire. We'll get a very clear and simple circuits, right? The voltage of the source are distributed on these three resistance. 3, 6, 3. So we are able to know the voltage across them according to the voltage division law are respectively 5 volts, 10 volts, 5 volts, right? And then we observed VC1. You see that VC1 is connected to the ends of the 6 omega resistance, right? So this is basically VC1. And we know that when t equals to 0 minus, VC1 equals to 10 volts, right? Yeah, what about VC2? When the switch is closed, VC2 is connected to the two sides of the 3 omega resistance. And similarly, we get that VC2 equals to 5 volts. Is it clear? Great. And what about the currents? The I, in this case, should be equals to I2, right? Because the capacitance is in open circuit and no currents flowing through it. We have I equals to I2 equals to 20 volts divided by the total resistance, which is 5 divided by 3 amps, correct? And I1 equals to 0. Great. So let's observe. Let's see what will happen next. When t equals to 0 plus, we need to make use of another property of the capacitance voltage. That is, VC is continuous. Why? Because VC is an integration of its current. And we know that the currents can only be finite, which means that the VC will change gradually. Intuitively, the function, the join of this VC should always be continuous instead of break somewhere, discrete, okay? So let's see what it means. It is continuous, means VC0 plus equals to VC0 minus, because it's a very, very short time, and it is too short for the VC to change. The voltage will remain the same. So we will easily get that VC1 is still 10 volts at this instance. VC2 is still 5 volts at this instance. All right. And what about current? The current of capacitance is finite, but it is not continuous. It can be continuous, but sometimes it is not continuous. So let's be open-minded and see what it is. When the switch is opened, this circuit, this path, this branch will disappear. And from KCL, we know that I equals to I1 plus I2, right? And from the KVL within the loop, VC1 plus 3 omega times I1 equals to 6 omega times I2 plus VC2, right? And we know that IC2 is 5 here, and VC1 is 10 here. And what we get? We get 2 equations of currents already. And then we have 3 variables, so we need 1 more. So we draw another KVL. 20 volts equals to I times 3 plus, right? Great. Combining these 3 equations, we get I equals to 7 over 3, 7/3, and I1. Great. Is it clear? Okay, check your understanding. I will ask one last question. What about when the time is long enough after the switch is open? What will be VC1, VC2, and what will be I1, I2? The first step is to remove the switch because it is already open, right? And then remember we said when it is a long time, we know the circuit is in steady state. And if the circuit is in steady state, we know that capacitance act like open circuit, right? So we can basically remove capacitance. And what it is? Clearly, the currents will be 0. You are correct. And since the current is 0, the positive polarity reference of the VC1 will be equals to the positive reference polarity of the voltage source. Why? Because no current flows through the 3 omega resistance. So the current drop, the voltage drop here is 0, which means that Vs equals to VC1. Because similarly, there's no drop here too. So the answer might be surprising. VC1 equals to Vs. And similarly, VC2 also equals to Vs. Okay? If you get the answer correctly, you understand it quite well. Okay? Great. I think it is good to stop here. And feel free to ask me questions in the office hour or emails or in Piazza, whatever. I know the new content, it's pretty intense. And it would take some time to get used to it and master the skills. But I'm sure you will do it well. Good luck.